Okay, so you've heard about virtualization, you've heard about networks. Those are the two pillars that the cloud rests on. So in this lecture, we'll talk about the cloud. And first, we'll talk about the structure of the cloud. So this is a public cloud. It's available over the internet to anyone who can pay. And the private cloud is owned by a single organization and is typically restricted to members of that organization. Uh, Public cloud has several characteristics. You only pay for what you use. So you're not buying computers, you're renting computers. The storage and computation services are elastic. What that means is that you can grow or shrink as your needs grow and shrink. Cloud, your use of the cloud is self-provisioned. You have an account and you can immediately begin using it. You don't have to wait for an organization to set it up. You want to allocate resources, so you can allocate resources immediately. And the cloud runs in a data center. So data center is somewhere in the order of 50 to 60,000 computers. It has independent power supply, independent security, independent air conditioning, and so on. The computers are stored in racks. The computers don't have displays. The computers don't have keyboards. So there is a keyboard that will control the rack, and uh, uh, the display is over the internet. And they're mostly commodity. So we'll talk about this in a minute, but computers fail no matter how reliable they are. And so in the cloud, they have to deal with failure. If you have to deal with failure, you might as well buy the cheapest computers you have. It may fail more frequently, but you know how to deal with it. And so the computers are, for the most part, commodity computers, with some exceptions. And data centers are collected. And so they can be collected into what's called an availability zone. So we're working from the bottom. We have a data center. There are geographically adjacent data centers, and adjacent in some sense, close anyway. And that gets an availability zone. And now let's collect a collection of availability zone, also geographically related, bigger now, and you have a region. The cloud providers maintain multiple regions around the world. So North America has multiple regions. South America has at least one. Europe has several. The Asia Pacific has a couple. South Africa has one. And so the number of uh, regions, it grows all the time. So now you want to allocate a new virtual machine in the cloud. So one of the things you'll notice when we talked about virtualization, we talked about virtual machines and containers. Uh, Cloud is specifically for virtual machines. Containers will run on top of the virtual machines, and we'll talk about that in the next lecture. But the kinds of mechanisms I'm talking about here are for the cloud, and the cloud manages virtual machines. So you want to request a virtual machine, and you specify a region, an availability zone. What type of virtual machine do you want? How big is it? Um, Maybe what kind of processor does it have? What image do you want to have loaded into that virtual machine? So we talked about virtual machine images. Okay, so you have to specify where it is. What are the security settings? And their collection of other parameters. And the cloud provider finds a physical computer with spare capacity in the specified availability zone in the specified region. And the hypervisor on that physical computer creates a new virtual machine, loads the image, and returns the IP address of the new virtual machine to the requester. So some offline discussion questions. What region are you in for AWS, for Google, for Microsoft? How many availability zones for each provider in your region? Why are commodity computers used in the cloud providers' data centers? And what are the parameters you have to specify in addition to the ones listed uh, in order to allocate a virtual machine? There are several different service models there within the cloud, again, within the public cloud. There's infrastructure as a service, allocate virtual machines, load virtual machines, execute virtual machines, build a network within the cloud, and so on. There's platform as a service. So platform as a service gives you a collection of dependent services that you can call. So you don't need to worry about all of the details. You can relegate that to some of the software that's in the cloud. And then there's software as a service, also called hosted services. And that's a total application. So it runs everything. You can think of Gmail, for example. Uh, you can think of customer management. You can think of invoicing, any kind of application. And platform as a service might be a reference architecture. So it provides you uh, some functions. It provides you a framework within which to put your specific functions, to customize it, and so on. So infrastructure as a service provides CPU, storage, and networks. And if you want to move a system to the cloud and you don't want to modify the system, then what you can do is allocate the appropriate number of machines in the cloud and just copy your service there, have it loaded. Platform as a service is an environment. It includes everything developers need to build, run, and manage applications, but it's not a total application. Uh, so all the things you need from servers and operating systems to all the networking, storage, middleware, and tools. So think of it as a collection of middleware. So it's useful if you're developing a system now. So when you develop a system, you have a variety of libraries. There'd be monitoring, there'd be security, there'd be storages, there'd be databases, and so on. Those are all part of the PaaS, but it isn't an application. You have to build the application. And then there's software as a service. Uh, and again, those are actual applications that are provided by the cloud provider or some vendor on top of the cloud provider. Sometimes the cloud fails. Okay. So if you search for cloud outages, recent cloud outages, you can get an enumeration. All the clouds fail. All of the things fail. Every vendor shows up in there, but it's rare. And sometimes just a part of it fails. This is much less rare. Here's a year in the life of a Google data center. There are a whole bunch of kinds of problems that can happen. This is an enumeration. Uh, the one that I like is the dead horse problem. Uh, so the dead horse the dead horse problem came about because a farmer wanted to bury a horse, had a backhoe, dug down, and he cut the power uh, to the data center. So, but there are other less trivial, less exotic types of things too. Amazon gives more specific statistics. So if you have 64,000 servers more or less, and each has 2 disks, then on an average day, 5 servers will fail and 17 disks will fail. So 5 out of 64,000 isn't a lot, but if you happen to be running on one of those physical machines that fail, to you it's a lot. And so when you design something for the cloud, you have to worry about failure. It's much more prevalent than it is if you're designing something for the laptop. And it gets worse than that. So just a sidebar into probability theory. So a normal distribution, everything is uh, evenly distributed, more or less. And so this is common. And the thing about a normal distribution is the mean and the median are the same. So if you know what the mean is, it's the average. If you know what the median is, it's the value of the middle. But there's something in the cloud called the long tail distribution. And in this case, some values are far from the median. and you get what looks like a long tail. And that will mean that the median and the mean are different. And so here's some experiments that we did 10 years ago now in Australia. And we issued a number of create virtual machine requests. We issued 1,000 create virtual machine requests. And somewhere around 5% of them were long tail. You can see the histogram here. And so you have to be aware of the possibility of the long tail. And that's because this is caused by the fact that you're digging deep into the computers, the cloud provider's network. So you make a request, in this case, create a virtual machine that gets passed on to something else. It gets passed on to something else. It gets broken apart, passed on to a couple other things. And it all has to work in order for you to get a virtual machine. And sometimes somewhere along the chain, the machine is out, the network is slow, machine just might be overloaded. And again, that will slow down the whole process. And that in the experiment we did, that's about 5% of your requests. So discussion questions: has there been a cloud outage in your region recently? What was the cause? Again, you can search for that. The Google failure statistics talk about a rack failure. What's a rack? What's a rack failure? Actually, I showed a picture of one actually, so that gets helpful. Okay, so one server may not suffice for all the requests for a given service. And so you have multiple servers supplying the same service, and you use a load balancer to distribute requests. So a server is registered with the load balancer. Requests come into the load balancer, and the load balancer distributes the request to the servers that it's managing. It also monitors the health of the servers and know which ones are healthy. So when you do a DNS lookup for a particular URL, then it will return the address of a load balancer as opposed to the address of an instance. It actually gets a little more subtle than that. It returns the address of a gateway. But for our purposes here, it returns the address of an IP of a load balancer. So let's see how that works. Client sends a message. The message goes to a gateway. And from the gateway, it goes to a load balancer. And from the load balancer, it goes to one of the servers. Okay, and then the server sends a reply back to the gateway, and it goes back to the client. So in that picture, there was no reason particularly why it went to the server in the middle. Could have gone to one of the other servers as well. But notice what happens with the IP as we do this. So remember, we talked in networking about the fact that IPs can be manipulated, and the client sends a message. It goes to the thinks it's going to the load balancer. It actually goes through the gateway. The gateway intercepts it, and it changes the source to be its IP. Remember that uh, the source of an IP message is where the response goes. So the gateway wants to get the response, and it sends the message to the load balancer. Again, the load balancer changes the destination now to be one of the servers, and it changes the destination IP, but not the source. The load balancer doesn't want to get a response. It sends it back to the gateway. And then the server sends a message back to what it thinks is the source. In this case, it's the gateway. And so the message goes back to the gateway. The gateway now sends the reply to the client. It has to have some way of mapping the message back to the original IP address. So IP addresses are both the destination and the source are manipulated for the purposes of scaling. The load balancer uses a variety of algorithms to choose which instance to use. One is round robin. You rotate the requests evenly. A second is weighted round robin. You rotate the request according to some weighting. So if one of the servers that you're that the load balancer is hosting, is managing, is twice as powerful as the other servers, it would get twice as many requests. So that would be a way of defining the um, the weighting. You could also hash the IP address of the source to determine the instance, which means that every request from a particular source always goes to the same instance. This is not recommended. But notice that these algorithms don't require knowledge of the service's load. That's done independently. Now, suppose the service is overloaded. So as the load grows, you may not have enough servers. And auto scaling is a mechanism provided by the cloud for creating new instances. So first you set up a collection of rules that determine under what conditions new servers are added, or you can also delete servers. And so let's see an example of that. You start with 3 servers and a load balancer. And now, because of the auto scaling rules, you have 4. So there are a bunch of questions. Who makes it or what makes the decision to add a new server? How does a new server get loaded with the right software? Because the server is just a virtual machine. And how does the load balancer know about the new server? And so the answer to this is the autoscaler, the answer to some of this. So the autoscaler monitors the CPU and I/O usage from each server. The server makes it visible, and the autoscaler gets it. And then it, has a collection of rules to determine whether to add a new server. For example, if one server has 80% utilization for 15 minutes, then that's overloaded. We need to add a new server. And now the new server is added. The other servers were initialized with what's called a load configuration. And the launch configuration, I'm sorry. So the launch configuration specifies what virtual machine to be added, what the security groups are, all the parameters that we talked about involved in loading a machine in the cloud. So the cloud keeps track of the launch configuration for a particular load balancer. When it needs a new one, it has that launch configuration and it applies it. And then the new server is registered with the load balancer, and it does that with the autoscaler. So it calls the autoscaler, says now instead of 3, you got 4. Here's the IP address. Start sending messages to the new one. Again, the process is reversed if you're going to delete one. So the other thing that can happen, again, we talked about failure. Instances can fail. So replies from server don't go through the load balancer. So you have to have another mechanism to determine the health of the servers, and that's a health check. So each server sends an I am alive message periodically, and this tells the load balancer that the service is healthy. If the server is not healthy, then the load balancer shouldn't send it any more messages, and so it doesn't. If the server fails, then the autoscaler will detect that failure and create a new instance, again, depending on the rules that it has. So some offline discussion questions. Why is it not recommended to use hashing as a load balancer distribution algorithm? How does the autoscaler know the launch configuration? Suppose the load balancer fails. How is that handled? Suppose the autoscaler fails. How is that handled? Again, failure can happen anywhere, and these things are virtual machines. So now let's talk about state. State is important for performance and logical reasons. And let's look at just some basic numbers for transferring data time. If you read 1,000,000 bytes from memory, it takes on the order of microseconds. If you have a round trip in the same data center, again, it takes on the order of microseconds, more microseconds. If you're going to read something from a solid state disk, it takes on the order of even more of microseconds, but even more microseconds. If you're going to read it from the disk, now you're up to milliseconds. If you're going to send a round trip intercontinental, it's on the order of 150 milliseconds. So consequence is storing state in memory is faster than storing it on a disk. Sending state from one data center to another within the same data center is faster than sending it to other data centers. And fast sending state across data centers is relatively slow. When I first saw, I mean, years ago, I first saw these numbers, microseconds, milliseconds. I said, boy, that's fast. But when you're doing it a million times, it's not that fast. It adds up. And so, how do you manage state from a logical perspective? So let's assume we have two clients and two instances of each server, and we want to count the number of requests from clients to servers. And you have three options. You can store the count in the clients, you can store the count in the servers, or you can store the count on a database. And if you examine it, then option one counts how many times each client calls a server, but it doesn't sum it across the clients. Option two counts how many times a server is called, but it doesn't, if a server is being load balanced, it might be just a fraction of the total number of calls. Option three lets you get a total count where you store the count on the database. There's no right or wrong answer. It depends to that how you do it. It just you need to be aware of the fact that state is important. How you manage state is important, and you have to decide what your application needs are. So why don't you code up something, code up those three options and see if what I said is right. Time a message round trip in the same data center. Is the number given correct? And so those numbers are a little bit dated. Data centers might be a little bit faster, but it's the order of magnitude that matters. It's microseconds, milliseconds. Okay, now let's talk about sharing distributed data. So we're in a distributed system. It may be that different portions of the system want to share data with each other, and you have a variety of use cases. There might be for a lock. It might be for some configuration information. It might be for discovery purposes. It might be for sequencing tasks, doing things in order. So there are really three options. There's a persistent database, and it takes time. If you look at the performance numbers to write things to a database, it means that you're writing it to a disk several times. But it's what you use for large data sets. And then there are distributed caching systems. Memcached is one, Redis is another, Elasticsearch is a third. Those are in memory and fast, but they're only good for small data sets. And failure will cause data loss. And then there's distributed coordination systems, in memory and fast, suitable for small data sets, but they're engineered for high availability. So let me talk a little more detail about Memcached. So that's a key value store. It's limited to a megabyte. Multiple servers do not communicate with each other. Each client stores the data on its server, or a server that is allocated to that. A server can store data for uh, multiple other servers. I mean, for multiple clients. Data is not shared. Okay, so if the clients want to share the data, they have to access the same data. And so session data can do this. Web page caching can do this. API caching can do this. Caching of objects such as images and files and so on. Can use something like Memcached. And there are patterns for dealing with the cache. So one is the cache aside pattern. So if you want to read from a database, first you check the cache. If cache is in memory, the database has to go over a network, so a cache will be faster. And then there's writing through cache, so you can You can update the cache. So what happens when you look at a cache is the problem with cache is to keep it synchronized with the database or with what you're caching. Doesn't have to be a database. Uh, and so one option is to write data to the database and the cache simultaneously. That's what this says. And then distributed coordination systems are fault tolerant with high availability. They manage the coordination among clients, and they make the operations appear atomic. So there are multiple open source implementations. This is one of those things you don't want to do yourself. It's like security type of code. It's tricky, I guess is the right word. So Zookeeper is one, etcd is another, Console is a third. These are open source. They've been used a lot. They're tested. Uh, Much better to do that if you want to have a distributed coordination system than to try and write your own. And so might be used for distributed locks, it might be used for service discovery, might be used for health checks. And let me just dig into distributed locks as an example. And so if you think about what a lock does, uh, it gives it makes it look like it can only be used by one user at a time, and it makes look like things are atomic. If you're in a distributed system, things are not atomic, so you need to make it look like it's atomic. And you would lock critical resources to prevent various kinds of race conditions. Okay, I mean, think about databases and updating databases. So a lock's a software construct, and associated with each resource is a lock bit. If the bit is 0, no one has it. If the bit is 1, it's locked. In practice, there's other information, but for our purposes, that's all we need. And the problems with locks is it can lead to deadlock. One problem. Two processes are waiting for each other to release critical resource. Process 1 gets a lock on one row of a database. Process 2 gets a lock on a second row of the database. They each want the other one to release its lock, but it's not going to release its lock until it gets both, until it gets a lock on both and can operate on both rows of the database, and so there's no progress. Another problem with the lock is that it's not atomic. So it's possible that while you're requesting a lock, you think you got it, but another process grabs it. And this can go on for a long time. And it's called live lock. Okay. And now suppose the virtual machine holding the lock fails, then the owner of the lock can never release it. Okay, so that's another problem. Now, if you have a distributed system, it takes time to send a message to create the locker. And so, time is a bad thing. It slows down your system. So the general problem is that you want to manage synchronization across a distributed set of servers, and the constraint is that up to half of the servers can fail. And so Paxos is a family of algorithms that use a consensus algorithm to manage concurrency. It's complicated and it's difficult to implement. That's what I say. Use an open source implementation. But as an example, suppose, so Paxos is based on the notion of a leader and followers. So the leader knows the state, the authentic state of all of the other servers. The others get it from the leader. Now suppose the leader fails. Then how do you choose a new leader and make sure that it's up to date with the authoritative state? And you can look this up. It's reasonably complicated. And so just as an example, Zookeeper is an example. Zookeeper was done by Facebook and Yahoo, I believe, because they're trying to solve the same problem. It's open source, so they don't get into trouble with antitrust. And so they collaborated to implement Zookeeper, and that's 10 years ago now, maybe. And so things are mostly consistent across all the instances. So there's a notion of eventual consistency, which is the lag time to do that, but that's relatively small. And Zookeeper keeps data in memory. That's why it's fast. It's limited to 1 MB. And it deals with managing failure as well as consistency. And it's done using a consensus algorithm. Its API is atomic. So all calls are atomic. They either succeed or fail. You don't have any partial state. The atomicity is done inside of Zookeeper. And so you create a lock by having a name. So client N would create lock one. And if it's successful, then it owns the lock. If it fails, somebody else owns the lock, number one. And so it gets put on a wait list and control is returned. So it isn't kept waiting until it gets the lock. It's informed when it has the opportunity to get the lock, so that avoids deadlock. When the owner of lock one releases the lock, then it deletes lock one. So since client N is waiting for lock one, it's on the wait list. Then the wait list is now all the clients on the wait list are now informed that lock one is available, and they all try and request it again. Well, one of them is successful. The others get put back on the wait list. And if the owner of the lock fails, and again, there's a health check to determine that, then the lock is released. So this solves the two problems that we talked about with distributed locks. So discussion questions. How does the Zookeeper check the health of its clients? What happens if one of the servers, not the leader, fails? And what's the comparison if you look up Memcached and Redis? What's the difference between the two of them? So finally, just mention security policies. So this is a set of rules that govern which accounts or services have access to which resources. And there are three aspects to this rule. There's identity. You need to authenticate the users. So authentication means they are who they say they are. There's access. You need to authorize the users, so they're allowed or disallowed. And you need to have some visibility so that you can trace. And we'll get into that when we talk about authentication and authorization later. The cloud services provides access control through something called IAM, Identity and Access Managers. And it's got a set of rules. You make an API call to a service. It checks whether you have the right to that service through the IAM. And Amazon reports that there are over 400 million IAM calls per second. So that's just a phenomenal number. So discussion, most cloud users don't use IAM services. Why not? And how does a client identify itself to an IAM service? So you need to do some research to find that. And that's the end of our lecture on the cloud.